All right, welcome back to Econ 2500. I want to go over this example here, example 1. Now I realize it's worked out here and it's worked out graphically, and I kind of show the steps, but I want to walk through each step and explain graphically what we're trying to do. So what I'm setting up first is this example where we're trying to determine the number of AS and HL spas. So I'm going to go off the idea that you can write out the linear program, and now I want to get into this idea of how to graph it out. So the steps to go from this part right here to this part right here is just simply write out each equation as a function of x2. So that should be x2 right there. I apologize. But so this can be x2 is less than or equal to 200 minus x1 for pumps, and so on and so forth. So it's these equations that I'm going to focus on first that I'm going to try to graph out in Excel to be able to give me the best idea as to what's happening in this graphical example. So I'm going to turn to a blank Excel spreadsheet here. All right, and I'm going to set this up, I'll zoom in just a little, as the number of AS spas. Okay, so that's my variable x1. I'm going to count from 0 to 200, counting by tens, just to kind of give me an idea of what's happening with this picture. Okay, now I'm going to write out my constraints. So my first constraint is pumps. And so if I remember back over here, the equation for pumps, it's these equations right here that I'm going to enter in and graph out each of these functions in a line graph. So for pumps, this is equal to 200 minus x1. Okay, that's the equation. We need to be less than or equal to that. For labor, the equation is 261 minus 3 divided by 2 times x1. And then for tubing, we're equal to 180 minus 3/4 times x1. And so now I can just copy and paste these all the way down. So again, each of these equations here is what's on the paper when I wrote out to graph out the constraints. Okay, and I take all those down, and now I can just highlight these, insert a line chart. I'll choose the top left option, and here I've created a graph. Here is LP example 1 graph. Okay, now just to kind of make things a little easier, I'm going to change some of the colors here. So I get that gray line, I'm going to change that to green. I get this orange line, I'm going to change that to red. Okay, now notice I have my words down here, so I'm actually going to change that whole column. So tubing, or labor, is red, so I'm going to change all of this to just red font. Tubing was green, so I'm going to change all this to green. And pumps was blue, so I'll change all this to blue. And that's just to kind of give me an idea and let me know what each of these things are doing. So this graph here is graphing out the constraints. Now notice the constraints, as we wrote it on our piece of paper, is each constraint needs to be less than or equal to. So x2 has to be less than or equal to 200 minus x1. Well, the blue line is 200 minus x1. I guess before I do it, let's actually select data and then edit my x-axis, sorry about that, to be at 0 to 200. Okay, and so when we talk about that pumps needs to be x2 less than or equal to 200 minus x1, is our pumps need to be along this blue line or less than the blue line. And so for our 3 constraints, if we identify our feasible region, we need to be below each of the 3 lines. So here that green line is going to be binding. We're going to go along that green line until we reach the kink with the blue line, then we'll go along the blue line. Notice now we're still below all 3. Find the kink there with that red line, and now I go all the way down to the red line until I reach the intercept right there. And that's what we're going to be focused on as our feasible region. Now, where are our possible solutions? Well, let's go ahead and graph out our profit function. So our profits is pi equals 350x1 plus 300x2. So I'm going to rewrite this. So I can rewrite this as x2 equals pi divided by 300 minus 350 divided by 300 x1. So that's simply just solving out this equation here for x2. And that's what I'm going to put over here. But notice I don't know what profits are. So I'm going to highlight this as blue, and I'm going to draw upon those profits, a number I put there for this equation. So profits equal, well, it's this. I'm going to anchor that, divided by 300 minus 350 divided by 300, that should be divided by, times x1. I hit enter, and now I drop that all the way down. And now I just enter my profits. So if I want profits of $50,000, then this will tell me the amount of profits. And so this will tell me my value of x2. And so I'm going to come over here to select data, and I'm going to add a new line, a profit line with the values right here. Okay, now it's yellow. I'm going to change that to black. So that black line is now my profit line. Okay. So as I put numbers in for my profit, it's going to show me the maximum profit, the possible profits. So if I want to make $50,000 worth of profits, I can make any combination along this line. So I can produce 80 units of x1 and about 70 units of x2. And that'll then satisfy my profit constraint. But if I want to make more profits, notice that that whole profit line right here, that's all in the feasible region. What happens if I want to make $51,000 in profits? Put 51,000. Notice that profit line shifted up just a little. And it's just a different allocation. Notice all of those are feasible points. And so the concept we want to do graphically is we want to keep increasing profits as long as we're in our feasible region. So if I go up to 52,000, I can still achieve that. 54,000. Now notice at 54,000, we're now at one of our endpoints here, if you will, an extreme value. 54,000 profits is when we produce only values of x2, so about 180 units of x2 and 0 units of x1. Because if we do that, we're now at the binding constraint of tubing. We're using all of our tubing. We have extra labor and pumps because we're below the blue and red line. But that's one of the possible solutions. But that's not the best solution because I can make even more money. If I type in 56,000, notice that while I can't produce these amounts anymore, I can produce anything along this part of the black line that's still below all three lines. And I keep increasing until I get to 60,900. And now at 60,900, I'm at this endpoint here where now my labor is binding. I'm using all of my labor, but I have extra pumps and tubing. But I could be along here where I could still increase even more. And so the idea here is we're going to keep putting numbers in for this profit function. So if I insert 64,000, well, now I'm right here at this intersection of the blue and green line. But notice that over here, and it's a little harder to see, is I could still increase that slightly more and be where that blue and red line intersect. So if I were to put in 66,100, that's the point where now I'm right at that intersection of the blue and red line. If I shift the profit line up even just a little, I'm now not satisfying my constraints. And so that's the thought process we go through of solving things graphically. Now if I were to hide that profit function, what the extreme point theorem tells us is there are three possible solutions to this. Or rather four, I apologize. So I'm going to circle those possible solutions. One possible solution, oops, let's take out the fill, is right here. I will even make that some bright. Make it yellow. No, oh, we can kind of see that. We'll even change the outline, make it a little heavier so we can, there. So here's one possible solution, is that extreme point right there. Another possible solution bad. I'm sorry. I'm trying to copy paste. We'll just insert another shape over here. Another possible solution is right over here. We won't format this since that's a problem. The extreme point says that right over there is another possible solution. That extreme. So we have the two corners. Another possible solution, I tried to copy and paste again, I don't learn the lesson, is these two interior kinks. So that's one. And here's the other. So that's what the extreme point theorem says, is there's four possible solutions. So what you have to do is, in a sense, one thing is just to find what each of these values are for x1 and x2, and then insert those into our profit function. And so this value, for example, is 168, I want to say. Yeah, is 180 units of x2. So we use 180 units of x2, but no units of x1, and that would give us that profit right there. This right here is 174, so if I use 174 units of x1 and no units of x2, then I would be at that margin there. And to find these points here, I just simply set the blue line equal to the green line. To here, I set the blue line equal to the red line. I solve for x1, I solve for x2. And I plug those into the profit function to see which is going to maximize my profits. For this particular example, the optimal solution is where the blue and red lines meet, meaning that we use all of our pumps and all of our labor, and we have tubing left on the shelf. And that's what's going to maximize our profits.